I'm going to explain in this screencast why the order of reactors for reactors in series does not matter when we have a first order reaction. Namely, we have plug flow and a CSTR in series. We can switch the order and get the same conversion. Or if we have two CSTRs or also two plug flow reactors in series, the order doesn't matter. So let's look at first order reaction, isothermal, just liquid phase, so there's no concern with volumetric flow rate changes. And the important aspect that determines this behavior is that for a first order reaction, the fraction that's converted is the same for a given reactor size and flow rate, independent of the actual feed concentration. In other words, if I increase the feed concentration a factor of 5, I'm still going to convert the same fraction in that reactor. And that's a direct result of the mass balances. So if we were to look at the mass balance for plug flow reactor, and that's a volumetric flow rate, the change in the concentration of the reactant with respect to cumulative volume minus K times the concentration. And when we solve this, what we end up with is that the concentration leaving the reactor, in this case be Ca1, is Ca0 e to the minus kV over volumetric flow rate. So you can see from this equation, the fraction converted is the same for a given volume, rate constant, and volumetric flow rate. So for example, let's assume for this plug flow reactor that we're going to convert 60% of the feed, so 40% leaves. And now we're going to look at CSTR. So we'll look at the mass balance for a CSTR. There's no accumulation. There's a molar flow rate in, which is a volumetric flow rate times the feed concentration, and then a molar flow rate leaving. And the difference is because this first order reaction taking place. If we solve this for Ca1, it's Ca0 multiplied by this term. Again, the fractional converted is the same, independent of the actual concentration. Just to make it easier to visualize, let's assume for this reactor that Ca1 is 7/10 of Ca0. So we're converting 30%. So let's look now at having these reactors in series. And the CSTR, Ca1, is 0.7 of Ca0. And the plug flow reactor, Ca2, is 0.4 times Ca1, which means Ca2 is 0.4 times 0.7. So we're converting 28%. Now let's look at what happens if we reverse the order. In that case, plug flow reactor Ca1 is 0.4 times Ca0, and Ca2 is 0.7 times Ca1, which means, again, 28% remains, that the outlet concentration from the system is the same, independent of the order of the reactor. And so you can see we're going to get the same result if we have two CSTRs in series, in the sense that Ca1 again is going to be 0.7 Ca0, and then Ca2, bigger reactor, so let's say it's 0.5 times Ca1. So Ca2 is 0.5 times 0.7 times Ca0. If we reverse the order, it's 0.7 times 0.5. So order doesn't matter for first order reaction for two CSTRs in series. And now let's briefly look at zero order reaction. So zero reaction, for a different reason, the order does not matter. And that's because for a zero order reaction, the amount converted is just proportional to the volume. So the total rate would be a rate constant times volume of a plug flow reactor, for example. say our first reactor, and a rate in our second reactor would be K times the volume of CSTR. So this rate is the total amount reacting in the reactor. So we can add rate 1 plus rate 2, and it's just the rate constant times the sum of the volumes. It does not matter the order of the reaction. For zero order, reaction rate's just proportional to the total volume.